Hello everyone. Okay, welcome back to the lecture. Okay, after the break. So we'll look at the another section, okay, which is more complicated. Okay, so we look at the calculation methods involving multiple effect evaporators. Okay, evaporation of solutions in a single effect evaporator. A major cost is the cost of the steam used to evaporate water. If we use one single effect evaporator, the cost of the process is majority of the cost came from the steam usage, the steam cost. Okay, now a single effect evaporator is wasteful of steam costs since the latent heat of vapor leaving the evaporator is often not used because at the top our vapor stream is still hot, right? It's still hot, it's still at the temperature inside the heating chamber. Okay, so we actually have a hot vapor coming out from the evaporator, but it's not being used. So to reduce the cost, okay, a multiple effect evaporators is commonly used in industry, which recover the latent heat of vapor leaving and reuse it for the next evaporator. So we have a multiple continuous multiple effects evaporator. Okay, so the design, the calculation is quite not straightforward. Okay, we have to do a lot of iteration. We have to do guessing and then recalculate until we get the right value. So in the first effect, raw stream is used as the heating medium to the first effect. So the first effect we can assume is like our single effects evaporator. Okay, which is boiling at temperature T1. Our datum temperature, we always choose the boiling point of the material at pressure P1. The vapor removed from the first effects is used as the heating medium, condensing in the second effects and vaporizing water at temperature of T2 and pressure T2 in this effect. So the vapor coming out of the first effect will be the heating medium for the second effect. The to transfer heat from vaporizing water at temperature T2 and pressure T2 in this effect, in the second effect. The transfer heat from the condensing vapor to the boiling water in the second effect, the boiling temperature T2 must be less than the condensing temperature, obviously. So the boiling temperature must be less than the condensing temperature. Okay, so this means that the pressure of P2 in second effect is lower than the P1 in the first effect. So the pressure will go down from first effect to second effect. Then in a similar manner, the vapor from the second effect is condensed and heating in the third effect. Hence, the pressure of P3 is less than P2. Okay, if the first effect is operating at 1 atmospheric pressure, absolute pressure, the second effect and third effect will be under vacuum. If first effect's raw dilute feed is added and is partially concentrated, this partially concentrated liquid flows to the second evaporators in series, which is further concentrated. So we get a more concentrated liquid coming out from the second effect. This liquid from the second effect flows to the third effect for final concentration. When a multi-effect evaporator is at steady state operation, the flow rate and rate of vaporization in each effects are constant. Let's look back at the diagram. So normally, okay, so this is a backward design. Okay, so we have a heat exchanger in each of the um, evaporator. Okay, so in our first effects, okay, we use our steam here, okay, to heat the material in the first effects. Okay, the vapor coming out from the first effects will be used to heat up the second effects. The heating of the heating medium of the second effect is coming from the vapor of first effects, and then this will be condensed and become condensate. Okay, and we collect this one. Okay, and then the vapor coming out from second effects will be used as a heating medium to heat the third effects, and then the vapor will be condensed and we can collect the vapor condensate, the condensed vapor. Okay, so finally we get the third from the third effect we get a very pure vapor coming up from here. Okay, and then you can see from first effect we get a slightly dilute product. Second effect we get a slightly more concentrated product. The third one will be the most concentrated product coming up from the evaporator. Okay, so this is a general schematic diagram of the multiple effect, three effects evaporator. Okay, now, right, the first step of calculation, the temperature drops. The first thing we need to consider is the temperature drops of the multi-effects evaporator. The amount of heat transfer per hour in the first effect of a triple effect evaporator with forward feed. Forward feed. Okay, we look at the case of forward feed. Just now it was a backward feed. Okay, forward feed. Okay, the Q1, U1, A1, delta T1 as the first evaporator. Okay, so delta T1 will be the difference between the condensing steam and the boiling point of the liquid. Our T1 always we pick the boiling point of the liquid or as our datum temperature. Assuming that the solution have no boiling point rise, remember if we have a very dilute solution without the presence of other solute, normally the boiling point is the same as water. Same as water, there will be no boiling point rise and no heat of solution or dissolution. Okay, letting the sensible heat necessary to heat the feed to the boiling point. Approximately all the latent heat of the condensing steam appears as latent heat in the paper. So there will be no heat generated and also no heat lost in the process. All the heat from the condensing the steam will go to the latent heat of vaporizing the vapor. Okay, so the Q2 equals to UA U2A2 delta T2. Same. Okay, so this is the heat for the second evaporators. Okay, now this same reason holds for the third evaporators Q3. Because no heat loss, there's no heat generation. So obviously the Q in the first effect is equal to the Q in the second effect, and is also equal to the Q to the third effect. So the three evaporators has the same amount of heat, heat transfer. Okay, the rate of heat transfer is the same in the three evaporators. Okay, so we can look at the sketch here. Okay, we have a feed. This is a feed forward evaporators. Okay, our feed here TF at TF go to the first effects, and then the vapor from the first effects at temperature T1, which is the same as the heating chamber or the boiling point of the liquid, will go to the second chamber to heat up the liquid in the second chamber. Okay, a second evaporator. The second evaporator will produce vapor that can be used as the heating medium to heat the third evaporators. And to have a vapor coming out from the third effects. Right, so the concentrate from first effect is slightly lower concentration. Second one will be slightly higher concentration, and third one with the most concentrated product. Right. Okay. Normally we keep concentrating the product, so output of the first effect will go to the second effect, the second effect will go to the third effect until we get a very concentrated final product. So the last pipeline coming out from the third effect is quite sticky or sometimes very viscous. Okay, so usually in commercial practice the area in all effects are equal. Okay, U over A equals to U1 delta T1, U2 delta T2, and U3 delta T3 because the A is the same. Okay, so from the first equation here, from the equation on the top here, because the Q, because of the A is the same, so we can simplify Q over A equals to the U1 delta T1, U2 delta T2, U3 delta T3. Hence, the temperature drops delta T in a multiple effect evaporator approximately inversely proportional to the value of U. Okay. Okay, if the U move here, so the delta T will inversely proportional. Is opposite. Okay, so larger delta T, lower U, okay, or lower U, larger delta T. Okay, now calling the sum of the delta T, the delta T in the three effects, the triple effects. The first effect delta T, second effect. So delta T will be a temperature between the um, what is the temperature different? Temperature different will be the between the TF and T1, right? TF and T1, TF and T1. Okay, this will be our T1 and T2. This one will be T2 and T3. The difference between delta T1 will be between TF and T1. Delta T2 will be between the T1 and T2 because this feed coming up from the bottom is at T1. Okay, and then the product coming out from the second effect is T2. So the difference will be T2 minus T3. Okay, then it's also equals to the because the steam Ts minus the condensate here. Okay, and it should be equal. The inlet steam temperature should be equal minus the difference minus the temperature of the condensate coming out from the final effects. Right, then the delta T1 is proportional to 1 over overall heat transfer coefficient for the first effects. Okay, you can see here delta T1 is proportional to 1 over U1. Okay, so to get this equation is actually you have to rearrange of the equation. Okay, you use the correlation here, correlation here, this correlation. Okay, so you have delta T2 is equals to U1 over U2 delta T1. Delta T3 will be U1 over U3 delta T1. And then you substitute all inside here, make all become delta T1, and then you rearrange. Okay, you should able to get this correlation. So not important. You should know that this is the correlation or relation, okay, between delta T1 and total delta T1 and also the U, the overall heat transfer coefficient in each of the effects. Okay, so similar equation can be written for delta T2 and delta T3. It's the same. Just you change the T1 become U1. T1 become T2, U1 become U2. All right. Now, capacity of a multi-effects evaporators. A rough estimation of the capacity of the triple effect evaporator compared to single effect can be obtained by adding the value of Q for each evaporator. Okay, so we sum all the energy, sum all the Q. Okay, so if we make assumptions that the U value is the same in each effect, A values are equal, actually we can just simplify the calculation of the heat is equals to UA sum of the delta T1, delta T2 and delta T3. If the U for all the effects is the same, the surface area of the evaporator of the triple effect, all the effects are having the same surface area, then okay, we can use this equation. If a single effect evaporator is used with the same area A, the same U, the same total temperature drop, we can use the same total temperature drop. This gives some same capacity for the as of multiple effect evaporators. The increase in steam economy obtained by using multiple effects evaporator is obtained at the expense of reducing capacity. Okay, so we can actually make it more smaller size. Okay, and okay, we can improve the steam economy. Okay, reduce the steam cost. Okay, so this advantage of multi-effects evaporators. Okay, now the value to be calculated, usually we want to know the area of heating surface in each effect. So we want to know what is the size of the evaporator, each of the evaporators, and the kg of steam per hour to be supplied. So we want to set our utilities, how many amount of steam needed to supply to our evaporator, amount of vapor leaving each effect. Actually in the last effect, we are collecting the product, right? So we need to know how much vapor coming out from the last effects, and also the amount of product coming out from the last effect. Okay, now the known value usually, okay, the steam pressure to first effects. Normally we have the steam pressure, the supply steam pressure we know. Okay, the final pressure in the vapor space of the last effect. So we coming out from the last effect, actually we can measure. Okay, so what is the final pressure? Okay, now the feed condition and flow to the first effects, we can set, right. We have a feed of certain solid content, okay, and then the flow rate of the feed. Okay, final concentration of the liquid leaving the last effect, physical property, okay, the enthalpy, heat capacity of liquid and vapor. This one you can find from the handbooks and appendix. So you can find from steam tables, you can find from the appendix values of the heat capacities. Now overall heat transfer coefficient in each effect, okay, usually it depends on the design of the evaporator. So each of the material, okay, because of the material selected for the evaporator, we can calculate the thermal resistance, right. From the thermal resistance, then we know from the size, then we know the overall heat transfer coefficient in each effects. Area of each effects, okay, we can assume, or we can actually know the size, okay, based on the dimension of the effects. Then the calculations are done using material balances, heat balances, the capacities equation, Q equals to UA delta T for each effect. Solving using try-error approach is common. So we have to do a lot of guessing. Okay, we guess the value, and then we substitute, and then we try, and then we check whether you can get the value that we guess. Okay, so from the known concentration, known outlet temperature or concentration and pressure in the last effect, determine the boiling point in the last effect. From the concentration that we know, pressure we know, right, the vapor pressure. From the vapor pressure we can determine the boiling point in the last effect. If a boiling rise is present, then we can use the during line plot that we learned earlier. Determine the total volume of vapor evaporated by an overall material balance. For the first trial apportion, or the first gas, the total amount of vapor among the three effects equal vapor produced in each effect. First, we start with V1, the vapor coming out from the first effect. V2, V3 are the same. We assume this one first. The V coming out here, the first effect, second effect, and third effects, they are all same. Okay, so first gas. Okay, usually they are the same. Usually they are at the same. Okay, so you make the first guess first, later we have to recalculate and confirm. Make a total material balance on effects of 1, 2, and 3, and obtain the liquid flow rate, mass flow rate for the first effect, second effect, and third effect, respectively, the L1, L2, and L3. Then we calculate the solid concentrate in each effect by a solid balance on each effects. Okay. This one we have to do material balance, the solid content. Okay, then estimate the temperature drops, delta T1, delta T2, delta T3 for the three effects. So we use this correlation that we mentioned just now. The delta T1 is proportional to 1 over U1. Delta T2 will be 1 over U2. Okay, delta T3 will be 1 over U3. Any effect has an extra heating load, such as cold feed, require a proportionally larger delta T. Okay, then calculation the boiling point in each effect. If a boiling point rise is present, we have to estimate the pressure in effect 1 and 2, and determine the boiling point rise in each of the three effects. Okay, now only a crude pressure estimate is needed, since the boiling point rise is almost independent on pressure. Okay, so maybe the first one we know, the second one maybe we can use the same. So it depends on the case. But the effects of pressure on the boiling point rise is less. So because the first effect will have higher temperature, second effect will be lower temperature. So first effect will have a higher pressure, second effect will be slightly lower, and third one will be much lower. So the impact of pressure on the boiling point rise is negligible. Okay, so we can assume same, the same boiling point rise. And then the sum of delta T available for heat transfer without the superheated is obtained by subtracting the sum of all the three boiling points rises from the overall delta T of Ts minus T3 of the saturation of the condensed steam. Okay, estimate T1, T2, and T3 from the important equation just now we mentioned. Okay, and then calculate the boiling point in each effect. Okay, now use heat and material balances in each effect. Calculate the amount of vaporized and the flow of liquid in each effect. If the amount vaporized differ appreciably from those assumed in step 2, step 2 and 3 can be repeated using the amount of evaporated calculated. Only solid balance is repeated in step 2. Okay, so after come here, we calculate back the balance. We check the balance of the heat and material. If not okay, not balanced, then we have to repeat back the second step, which is here, the V1, V2, and V3. Maybe it's not equal. We have to check back the V. Right, now calculate the value of Q transfer in each effect using the rate equation. Q equals to UA delta T, the heat transfer rate equation. For each one, calculate the area of A1, A2, and A3. Then calculate the average value, average surface area, A1 plus A2 plus A3 divided by 3. If this area are reasonably close to each other, the calculation are complete and the second trial is not needed. Okay, close means around 5 to 10% same. Okay, near. Okay, if not nearly equal, the second trial should be performed as follow. Start with to start trial 2, use the new value of L1, L2, L3, V1, V2, V3 calculated by the heat balance in step 4 and calculate the new solid concentration in each effect by a solid balance on each effect. You use the value that calculated now to start all over again. Start all over again, assuming the L1, L2, L3 that calculate now is the initial one, which recalculate everything. Okay, obtain the new value. Okay, we have to estimate the new delta T1, delta T2, and delta T3. So we make a prime there. So we ratio with the surface area that we calculated in the first trial. Okay, so we use the first trial surface area as a ratio. Okay, based on the surface area, we ratio the delta T1 prime, delta T2 prime, delta T3 prime. Then we sum all the delta T1, delta T2, delta T3 must equal, and the original delta T total. So you must add the delta T1, delta T2, delta T3 prime. E must equal as the original delta T. If not, proportionately readjust all the delta T values so that the total is equals at the sum of delta T initial. Okay, then we calculate the boiling point in each effect. Because we have the delta T now, we can calculate the boiling point. Then if boiling point rise is present, then use the new concentration, determine the new boiling point rise in the three effects. This gives new value of delta sum of the delta T available for heat transfer by subtracting the sum of all three boiling point rises from the overall delta T. Okay, so we can calculate the new delta T again. Sum of delta T value just calculated must readjust to the new sum delta T value. Then calculate the boiling point in each effect. Use the new delta T value, repeat the calculation starting from step number 4. 2 trials are usually sufficient so that the areas are reasonably close to being equal. So if the total area is almost equal, then we can stop. Okay, so let's have a look whether we understand the concept or not. Let's start with example 4. Okay, now estimate the requirements of steam and heat transfer surface of a triple effect evaporator. Okay, now the evaporating temperatures in each effects from a triple effect evaporators evaporating 500 kg per hour of a 10% solution up to 30% solution. Steam is available at 200 kilopascal gauge and the pressure in the evaporation space in the final effect 60 kilopascal absolute. Assume that the overall heat transfer coefficient are 2270, 2000 and 1420 joule per surface area per second degree Celsius per Celsius in the first, second and third effects respectively. Neglect the sensible heat effects and assume no boiling point elevation and assume equal heat transfer in each effects. Okay, so we can solve this. So first of all, we solve the material balance first. Okay, material balance first. We have feed 10%. Okay, you go back to the question. It gave you the feed is 10%. This is a desired final concentration. After it come up from the evaporator, the product should have 30%. Okay, and then so we assume total is 500, right? The stream coming in is 500. Okay, in 1 hour time. Okay, so 10% is solid. 10% is actually the concentration, right? It's solid. So the liquid will be 450. 50 over total, 50 over 500 is 10%. Total is 500, right? So we make the 10% coming out from the total is solid 50 lah. Okay, if the concentration is 30, okay, so at the final, since the solid will not disappear, only the liquid, the water being evaporated. Okay, so the solid at the end of the three effects will remain the same at 50. That the concentration is changed to 30. So to make the final concentration 30%, the solid still remain 50. The liquid volume should be reduced. So we have to calculate the x. So you should have x here, 50 plus x, and then 50 over 50 plus x, okay, equals to 30%. So we adjust so that it will go to 30%. So if you put 50 over 167 is 30%. It's 30%. Okay, correct, right? 50 over 167 is about 30%. Yeah, correct. Let me say 50 over 167. It's 30%, correct. Okay, so it's 30%. Now, okay, now the heat balance. From steam table, the condensing temperature of stream at 200 kilopascal is 134 degrees Celsius. Okay, so in the first effect, the steam is coming in at 200 kilopascal, which we have the information. Okay, if you check the steam table at 200 kilopascal, the boiling point is the boiling point is 134, and then the latent heat you minus the saturated vapor minus the enthalpy of the liquid, then you get 2164 kilojoule per kg. Okay, now the evaporating temperature in the final effect under pressure of 60 kilopascal, which is already given in the question. You check in the steam table. The boiling point should be 86 and no boiling point rise, and latent heat should be 2294 kilojoule per kg. Okay, so you check in the, let's say we try in the steam table. Go to the steam table. We go to 60 kilopascal. 60 kilopascal is somewhere here, somewhere between here. So it's around 86. You calculate by interpolation, you get 86. And then from here, you calculate the interpolate here, interpolation here, and then you minus. Okay, so we'll get the value of 2294. Okay, then we have the value, when we have to assume Q1 equals to Q2 equals to QT3. Okay, and UA equals to UA delta T of the three effects are the same, and then the overall delta T is equals to the sum of delta T is equals to delta T1 plus delta T2 plus delta T3, which is equal 134. Okay, which is the uh, the steam boiling point minus the which is the this one, get as a question, which is this one, Ts minus T3. Okay, so we minus Ts minus T3. Okay, so which is equals to 48 degrees Celsius. Okay, if all the surface area are the same, okay, and then delta T2 equals to U1 delta T1 over U2, delta T3 equals to delta T1 delta T the delta U1 delta T1 and U3. This is based on this correlation. Okay, using this one, so it's between delta T2 and delta T1, delta T3 and delta T1. So we take this one and substitute inside here. Okay, and we rearrange, we'll get this delta T1 factorized, and then it should be equals to 48 when we calculated. It's between the steam temperature and also the temperature of the condensate coming out from the third effects. Okay, so then we have all these, we substitute the U value is given in the questions, then we equal to 48 and rearrange, we get our delta T1 equals to 12.9 degrees Celsius. Now we have our delta T1. Then from there we can calculate our delta T2, since from here delta T2 is U1 delta T1 over delta U2. So from here we can get delta T2 equals to 14.6 degrees Celsius. Then we can do the same for delta T3. Okay, we calculate the value from the correlation above using this one. So we can get delta T3. Okay, then so the evaporating temperature first effects is at we calculate just now, delta T1 is 12.9. Okay, so we should minus this one. So this is the boiling point, the temperature inside the heating chamber. Okay, then we search the latent heat. Okay, from steam table at 121 degrees Celsius, you should get 2200 kilojoule per kg. In effect 2, also same thing, we know the delta T2 is 14.6. Okay, and then the temperature coming out from delta T1 is 121. So the feed temperature of the second effect is 121 minus the delta T will give us the temperature inside the second effect, which is 106.5 degrees Celsius. From there, we search in steam table, we get our lambda. Our latent heat is 2240 kilojoule per kg. Then we look at the third effects. The temperature in third effects T3 is equals to the outlet of the second effects, right? The T2. Okay, T2 minus the delta T3. So it gives us 86. So this is the temperature inside the third heating chamber. Then from this is the boiling point in the third, the liquid in the third chamber. Okay, the third effects. Okay, then we search in steam table for this temperature, we get 2294 kilojoule per kg. Okay, now so equating the quantities evaporated in each effects and neglecting the sensible heat changes. Okay, let's say W1, W2, W3 are the respective quantity evaporated in first effect, second effects, and third effects. So this is the vapor, evaporated, our V1, V2, V3 actually. So the V quantity of steam condensed per hour in the first effect. Okay, so the first effects, okay, times the latent the enthalpy by times the enthalpy. The mass times the enthalpy is the energy in the first effects. Okay, then the second effects also based on the latent heat here. The third effects will be the latent heat here, and then this is the condensate amount. Okay, so if you look back, Okay, we have the amount here. Okay, W1, W, sorry, W1, okay, W2, W3, wait, okay, sorry, W1 is here, W2, W3, okay, and steam condensation per hour in first effect, okay, so this one is WS here, wait, evaporated, okay, now, sorry, okay, sorry, go back. Okay, here W1, W2, W3 are the quantity evaporated in the first, second, and third effects. WS is the steam condensed in the first effect. Okay, so if you refer to the diagram, so WS is the first one here, WS, and then W1 is here, W2 is here, W3, or V1, V2, V3, and here is actually our WS, okay. So the energy, okay, evaporated is actually equals to the energy uh, condensed. Okay, then the sum of the quantity evaporated in each effect must equal to total evaporated of three effects. Okay, so just now we have the balance, right? So total vapor evaporated is 333 kg per hour. Okay, so the amount of W1, W2, W3 should be equals to 333. Okay, so yeah, so you need to do uh, guessing. Okay, guessing to make W1, W2, W3 equals to 333. So you have to adjust the value. Okay, adjust the value so that W1, W2, W3 will give you 3333. Okay, and W1 should be higher than W2, and W2 should be higher than W3. Okay, so we can adjust this value, okay, until we get 333. Okay, okay, then uh, if required, okay, why 1 1 1 1 2 yes, correct. Okay, so this amount evaporated, this is amount condensed. Okay, now if required 115 kg steam to evaporate a total of 333 kg of water, then 0.5 kg of steam per kg of water evaporated. Okay, correct or not? Correct. Okay, so it'll be 115 over 333. Okay, now heat exchange surface, writing a heat balance on the first effects. Okay, so the W1 H1 is equals to UA delta T. Okay, so okay, so the first one we assume is 113. We multiplied with the latent the enthalpy. Okay, and then this is to make it to joule, and then this is to make it to second. Divide by 3600. Okay, so it will be joule and second. We adjust. Okay, from kilojoule per hour. Okay, we change to joule per second. Okay, so this is the UA, the U value we have, the A surface area, and the delta T we have for the first one. Okay, so we get the value of the A equals to 2.4 meters square. Okay, now since we at beginning we say the surface area are the same, so the surface area of the second effect and third effect are also the same. So total surface area is 7.2 meter square. Okay, then okay, okay, then we solve the problem. Is it? Let me see. Okay, assume no boiling point. Assume no steam is available. estimate the required steam and heat transfer surface area. Okay. Okay. Okay, so this is the amount of total area we have, 7.2 meters square. Okay. Okay, so we are done. Now we have solved the surface area and we have determined the composition of the steam. All right. So next we go to the last section. Go to the last sections. Okay, let's look at the last section is the condensers for evaporators. Okay, so in multiple effects evaporators, the vapors form the last effect are usually leaving under vacuum, which is less than 1 atm, because the pressure is dropped right from the first effects to the second effects, and then when you reach the third effects the pressure is much lower than the first effects. So these vapors must be condensed and discarded as a liquid at atmospheric pressure. This is done by condensing the vapor using cooling water. The condenser can be a surface condenser, where the vapor to be condensed and cooling liquid are separated by a metal wall, or a direct contact condenser, where the vapor and cooling liquid are mixed directly. Okay, so this is a forced circulation evaporators. Okay, I'm showing the figures here. Okay, so you can see when you're coming out from the evaporator, for example, this is a heat exchanger. Okay, so we need to introduce cooling water to cool the vapor, and then it start to condense and we can collect out from the, this is the separator. The vapor, hot vapor come out here, and then we have cold water, and then we can condense that and get condensate out from the condenser. Okay, so this is one example of the condenser, right? Now surface condenser, it is used when the actual mixing of the condensate with condenser cooling water is not desired. Okay, so a shell and tube condenser or shell and tube heat exchanger used as the condenser with the vapor on the shell side, cooling water in the multi-pass flow on the tube side. Non-condensable gases are usually present in the vapor stream. If the vapor being condensed is below atmospheric pressure, the condensed liquid leaving the surface condenser can be removed by pumping, and the non-condensable gas by a vacuum pump. If it is more expensive and use more cooling water than the direct contact condenser. Okay, so of course when we have indirect we have more thermal resistant, so this one will incur more cost, as we need more energy to and more metals, and then the cost of the device is higher. Okay, now this is a direct contact condenser. Cooling water directly contacts with the vapors and condense the vapor. The common type is barometric condenser. Okay, as shown in the figure below here. Okay, so we have water vapor coming out from the evaporator. Okay, and then we have cooling water spraying through here. Okay, so it start to condense, and non-condensable one will discard out of the discard point. The condenser is high enough above the discard point and in the tailpipe, so that the water column established in the pipe more than the condensates for the difference in pressure between the low absolute pressure in the condensate and the atmosphere. Okay, now the water is discarded by gravity through the seal port at the bottom. A height of about 10.4 meter is used. It is inexpensive and economical of water consumptions. So it can maintain a vacuum corresponding to a saturated water temperature within about 2.8 Kelvin of water temperature leaving the condenser. Water consumption can be estimated by a simple heat balance. Okay, so if the vapor flow to the condenser is V and temperature Ts and water vapor is W, at an entering temperature T1 and leaving temperature of T2. Okay, so we can get a balance for the condenser, okay, which is the vapor coming out from the evaporator. This is the energy required to condense. Okay, MC delta T, right, to condense the vapor, plus, okay, the vapor plus the uh, condensed flow rate as with Cp and delta T. Okay, so we can rearrange the equation, become like this. Is it correct? T2, T1. Oh, T2. This is T2. Okay, this is the wait this is the entering. This is a leaving. This is leaving. The V of the uncondensable times the water. Okay, Cp T2 minus, what is the T2? Leaving temperature, the leaving temperature. So we can solve by using this heat balance to determine the vapor flow rate. Vapor flow V, condense and water flow, entering temperature and leaving temperature T2. Okay, so we want to find the V and W, the rate, Okay, leaving temperature T2. Okay, so this is a balance for us to find water consumption. We want to know how much water required. Okay, okay, okay. So this equation can be used. So Hs is enthalpy from the steam table of the vapor, Ts, and then the pressure in the vapor stream. Solving the equation, the equation by ratioing the water to vapor amount. Okay, so it's basically calculating from here. The enthalpy minus Cp delta T and also Cp delta T for the vapor. Above is for water, below uh, is for vapor. Okay, so the non-condensable gases can be removed from the condenser by a vacuum pump. By vacuum, we can suck up the uh, uncondensable gases. Okay, so basically this is all on this topic. So uh, let's see. You have question, you can always email me and ask questions. Okay. Before we end this session, I also wish to say thank you lah. Okay, you try the tutorial question. If you have problem, please feel free to contact me. So these are the uh, tutorial questions that you have tried, and then if you have problem, please let me know. The last question is on multiple effects evaporators. So try and see whether you can get the answers by trying all the principle that we discussed just now. Okay, thank you for listening.